Okay, hello everyone. So I would like to thank the organizers for the invitation. It's a real pleasure to be here with you. So I am Gonzalo Manzano. I am coming from the Institute for Cross-Disciplinary Physics and Complex Systems, IPhT, in Mallorca, Balearic Islands in Spain. So Mallorca is a small island in front of the east coast of Spain. And we are in a kind of small medium institute there, which is part of the Université of the Balearic Islands and the Spanish Research Council. Today I am going to talk about stochastic thermodynamics in quantum jump trajectories. And I would like to cover three kind of parts. So the first one is entropy production and the second law along quantum jump trajectories. The second one is the use of martingale process in order to get some extra insights on entropy production. And the third one is what happens to the thermodynamics when we have inefficient detection of the jumps. So let me just start with a brief introduction. So stochastic thermodynamics is a framework that has been developed over the probably last 20, 30 years in order to handle the thermodynamics of small fluctuating systems with a lot of success. And one of the main successes has been the refinement of the second law of thermodynamics at the level of fluctuations, introducing new constraints that the entropy production should obey during thermodynamic processes. And it has been applied to a broad range of systems. Here I just put some of them, like for example, electric circuits, colloidal particles that are trapped with optical tweezers that can be manipulated. Also molecular motors, like for example, this ATPase rotatory motor, or also nanoelectronic devices, like quantum dots, single electron boxes, etc. However, so here you can see also a review on the stochastic thermodynamic experiments. However, there are many systems in which, apart from fluctuations coming from an external environment, usually a thermal environment, you have also some non-trivial quantum mechanical evolution. So for example, you can think of light harvesting complexes, where you have some absorption of photons that are transmitted to until to reach some reaction center, so that the evolution is coherent. We have been seeing also during this morning experiments in cavity and circuit QED experiments. Also for the case of quantum thermal machines, where here I just showed two of the prototypes that has been implemented in the laboratory with MV centers in diamond or with trap ions. And also like in the case of quantum computers, like for example, the IBM quantum computer. So in all these systems, we have both fluctuations from the environment, thermal fluctuations, and also some quantum mechanical evolution that that is playing some non-trivial role. So the framework that I'm going to explain is allow us to assess fluctuations in these kind of processes. So the idea, in order to assess fluctuations, is that you may need two ingredients mainly. So the first one is what is called a two-point measurement scheme, which means that if I have some Draven dissipative process of which I want to characterize the thermodynamics, so I will need to introduce some projective measurements at the beginning and at the end of the process in order to assess for quantities like the energy changes in my system or the entropy changes in my system at the level of fluctuations. So here I will assume that we have projective measurements of some generic observables, so not necessarily energy, not necessarily the Hamiltonian of the system. And in principle, the measurements that will be most informative, indeed, will be the ones that commute with the density operator of your system at the beginning and at the end. In that case, at the average level, you will not modify the statistics. So it's as if those measurements were not being there. But of course, that makes a difference in the case of the selective evolution. And I will also assume that the driving dissipative process in the middle is Markovian. The second ingredient is a continuously monitored scheme. And here is where quantum trajectories came. And why is that? It's because if I have some driven dissipative process, I will have quantities like work and heat that do not depend just on the initial and final state of my system, but it depends on the path that my system follows over time. And this is why I will need some continuous monitoring of my system. So in particular, if I want to, for example, assess the heat over my evolution, I will need to continuously monitor what is leaking out my system, what is the energy my system is leaking out. So, for example, you may have some photodetector, and then you will see some trajectories of the photon number in the case you have a cavity, etc. So some pioneering works using these kind of two ingredients for the framework are the works by Jordan Horowitz and by Hekin and Pekola in 2012, 2013. And we have been we wrote some mini review about all this framework in this reference here, in which most of my talk will be based. Okay, so I will use quantum jump trajectories to describe the evolution of my system conditioned to the monitoring. So let's just start by writing down what will be the average evolution, like given by some Lindblad master equation, in which we have some Hamiltonian and some dissipators with some Lindblad operators Lk. So here you will notice that the Hamiltonian and the Lindblad operators may depend on some parameter lambda, which is just a control parameter. So we are intended to change this parameter over time in order to perform some protocol on our system. So in the following, I will forget about this dependence, but just to make you clear that that should be there everywhere. So one of the conditions we are going to assume is that the Lindblad operators in the master equation come in pairs in which verify this relation here. So this relation here is called local detail balance. It ensures essentially that when you froze the driving of your system, and if you have, for example, one thermal reservoir, your system will thermalize to that. Okay? Here in this local detail balance relation, you can see that there is some numbers, delta Sk, that will account for the heat exchange with the environment during over any of these when any of these jump operators occur. So essentially, just to give some basic example, so if you have some emission operator, you will have also some absorption operator, and the two will be related by the dagger operation with some exponential of minus the frequency divided by the temperature. Okay, so this is just a symmetry that the Lindblad equation gets when you impose it, that it has to thermalize under the specific conditions. So that will be the average evolution, but now we are interested, of course, in the monitored evolution. So we will use an stochastic master equation for that, which is essentially, as we have seen during the lectures in the mornings, it is the evolution of the system conditioned on the measurement record that you obtain. So in this talk, I will center on quantum jump trajectories, which mean a particular measurement scheme for your system. And this leads to this kind of stochastic master equations, in which you still have this Hamiltonian term, and then you have, instead of the dissipators, you have two different terms. One, which goes with this first term, is a smooth evolution operator. So as you can see, it goes with dt. And it is responsible to some non-unitary evolution over your system, which is, however, smooth. And on the other hand, you will have some abrupt changes in the state of your system that are related to the jumps, or the so-called quantum jumps, and each of them is related to one of the Limrat operators in the master equation. So yeah, as you can see, these go with this dn, which are stochastic Poisson increments. They can take either value 0 or 1, and they essentially signal the jumps over the evolution. They fulfill this property, so dn squared is dn, and then you can operate with this kind of equation. So here I just put some example of a qubit in which you have some driving, so it will do like Rabi oscillations. And then you have some jumps, so the evolution starts close to 0, goes up, and at some point you have some emission of a photon, then you go back to 0, and you start going again. No? So that will be this smooth non-unitary part of the evolution, while this red line will be the quantum jump. So what comes out from this stochastic master equation is essentially a measurement record. So in the measurement record, we have information about the outcomes of the measurement along the evolution. In this case, combining it also with the two-point measurement scheme, we will have some outcome for the initial projective measurement on our system. We will have also the final projective measurement on our system, T and tau. And then we will have a set of jumps that are occurring at different times during the evolution, associated to the different Limrat operators, so K1, K2, etc. Using this measurement record, we can also, on the evolution, we can also construct some trajectory operators. So these trajectory operators allow us to reproduce the state of the system once we know what is the measurement record that has been obtained. And they will be a combination of some non-unitary smooth pieces intersected by the quantum jumps, by the Limrat operators. So the state of your system at the end will be just the result of applying these trajectory operators over the initial state divided by the probability, which will be just the trace of the numerator. Okay, so then, so what we call a thermodynamic process in this context is the following. No? So if you look again to the average evolution, you will have some initial distribution for your system, rho 0, which you can decompose with some projectors and probabilities. So you just miss the composition. The evolution will be given by some Limrat equation, and you will get some final distribution, rho tau, which you can also decompose. So in general, as I commented before, we have both the Hamiltonian and the Limrat operators eventually depending on some control parameter, and this control parameter will be changed during this evolution from 0 to tau according to this driving protocol lambda. So for assessing the trajectories, we will first perform the initial measurement. We get some outcome n0. Then we will have this trajectory in which we are varying the Hamiltonian and so on using this driving protocol. So there will be some heat out, there will be some work, and then we again measure at the end. Here, as you can see, so we will measure at the beginning with the projectors of the initial distribution, and at the end with the projectors of the final distribution. So we are assuming like the less disturbative case. So here we can define then a probability of any trajectory. So that will be the path probability, right? So starting from this eigenstate n0, we will apply the trajectory operators, and we will apply the projector at the end. So that will be the conditional probability to obtain n tau, given that I start with n0 and I did all this trajectory according to this record, multiplied by the probability to start in this. Okay, so how we characterize the energetics and the first law during such a process? So one can, first of all, compute what is the energy change in the system during one of such trajectories. In order to do that, we just use the expectation value of the Hamiltonian at the final state minus the expectation value of the Hamiltonian at the initial state, right? So notice again that these projectors are not necessarily in the energy measure, are not necessarily in the Hamiltonian basis. So we can have some superposition of Hamiltonian again. So the stochastic first law in this sense will be to split these energy changes during the trajectory into work contribution and heat contributions from the reservoirs. So in order to characterize the heat, what we will assume is that we will use the energy which is associated with the entropy exchanges with the environment. So that we are going to collect all the entropy changes with the environment occurring during the jumps, and we will sum them. And that will be essentially the heat during the trajectory. Then we can also define the work coming from the driving, no? Because we are changing the Hamiltonian according to some protocol. So this will be this term here. So we will use the derivative of the Hamiltonian, and we calculate the expectation value with the conditional state of the system during the trajectory. This is essentially the input work, the mechanical work we are doing. Then in the case we have also like exchanges of particles, we will have also some chemical work during the trajectory, which will be also related to the jumps. It will be given by the fluxes of particles when you have like different chemical potentials. So this mu are the chemical potentials, and this n will be the number operator of the particle. So this for example, in cases of solid state, when you have like quantum dots and so on, you may have also these fluxes of particles on the top of the fluxes of energy. But then, if we just sum these three contributions, it happens that we don't get the full change in energy during the trajectory. And so what is the missing part here is what we have been calling measurement energy or measurement work. Okay, this is the mismatch energy that will make this, will turn this into an equality. So this is essentially a quantity which is just quantum. So it disappears if the trajectory is classical. So if you have just some stochastic trajectory between discrete states. And it has these two terms. So this first term that acts during the no jump periods, and this other term that also acts during the jumps. So in both no jumps and jumps, you will have this measurement energy coming in. Also, what is relevant is that the average of this guy is 0. So it only affects fluctuations. It's only a term that appears during the stochastic energetics. If you just look to the average evolution, you will not get this. So, and as I said, if the trajectory is classical, which that will be when the state of your system is always an eigenstate of the Hamiltonian or an eigenstate of this operator, then both parts here will go to 0, and you will not have any more this contribution. And finally, you will have also similar contribution, because this is during the dynamics, during the monitoring dynamics, but you will have also similar contribution for the final projective measurement. So just to give an example, just consider the dissipative driving qubit, in which you have just some two-level system, which is driven by an external laser, which is weakly driving in this case. So you have lambda operators proportional to sigma plus and sigma minus, and the entropy changes will be just the energy spacing of the qubit divided by the temperature. So in a trajectory like the one I commented before, what will happen is, like, for example, if you see this evolution, so the change in energy of the system starts being 0, it starts to increase as your system go up. But then when the jump occurs, the reservoir absorbs an entire quantum of energy. But however, the energy of the system, the expectation value of the energy in the system was not, so it was not in the excited state. It was like in a superposition, like towards the middle. So essentially, that will mean that in order to complete this, this quantum of energy absorbed by the environment, you will need some work that we associate with this measurement, with the monitoring scheme. So here in this plot, you can see just the sum of the total contributions to the work, the heat, and the change in the energy. And here you can see how this splits in this energy for the measurement and the energy of the driving. So during this period here, you are performing some work because you are driving your system and your system is going up in the Bloch sphere. But then when there is this jump, then you will see acting this work or energy from the measurement. Okay. Also during the no jump evolution, you see, so this is almost flat, but this is a bit tilted. So this means that you still are performing some small amount of work of this type during the no jump dynamics. But of course, the most prominent cases is when you have these jumps, when you appreciate these abrupt changes in the work. Okay, so that was for comment on the first law during the trajectories. Now let's go to the second law. In order to assess the second law, we are going to compute what will be the irreversibility during the trajectory. In order to do that, we have to define what will be the time reverse process in this setup. So the time reverse process will start in the final state of the forward, and then it will evolve according to another Limblad evolution until some final distribution, which in general will be different from the initial distribution of the forward process. And how is characterized is this time reverse Limblad evolution. So essentially, you will have the time reverse driving protocol acting on it. Okay, so this will generate just same Hamiltonian and Limblad operators, but the driving is just time reverse. Okay, so I am using here around this anti-unitary time reversal operator theta, which is responsible of changing the sign of the quantities that are out under time reversal. So for example, if my Hamiltonian will depend on momentum, applying theta and theta dagger will change the sign to the momentum, but for the position it will remain the same. Okay. In the most simple case, you may assume just Hamiltonians and Limblad operators that just depend on even quantities, so you don't need to change the sign. So in this time reverse trajectory, we then will first measure using the projectors here. Then we will evolve according to this time reverse dynamics using this time reverse driving protocol, and then we will measure again. Now here we use the projectors of the initial state of the forward. Okay. So now we can ask. The idea here is to ask what is the probability to have a trajectory which is essentially the trajectory reverse from the one we said before in the forward process. Okay, so with the time reverse process, you can also generate, you can sample trajectories and everything, but we are particularly interested in what is the probability of having exactly the reverse trajectory we observe in the forward. So this will be characterized as this. So we have the final outcome of the measurement, and then the jumps in reverse order. And here it's important to say that in this time reverse trajectory, of course, if in the forward trajectory you have a jump up at some instant of time, at the same instant of time in the time reverse you will have a jump down, and this is why I put here this till case, okay, because So a jump up corresponds to a jump down in the time reverse. Then you can also calculate what is the probability of this reverse trajectory using the same methods. And then you can now go to the stochastic entropy production. So the stochastic entropy production is this object here. So on the one hand, is the log ratio of the path probabilities to obtain some trajectory in the forward process and the reverse trajectory in the time reverse process. And it happens that it is equal to the change in the system entropy plus the entropy fluxes coming from each reservoir, which are just the heat over the temperatures. Here beta is the inverse temperature. So system entropy change is characterized by the change in the surprisal during the evolution from the initial to the final states. And as I said, the entropy flow will be just heat over temperature, which is, as I said before, this sum of all the change in entropy due to the jumps during the evolution. So something that I want to remark is that here we have this equality. So this equality is very important, I would say, because it is relating two different things. So on the one hand, it's relating this object here, which is just information theoretical object. It just tells us how likely it's to have a trajectory in the forward process with respect to the reverse trajectory. And on the other hand, we are relating this is a measure of irreversibility, with the energetics of the system. So here we have change in entropy and heat exchange with the reservoir. So we are establishing a link between information theoretical quantities, irreversibility, and energetics, heat exchange, energy exchange with the thermal reservoir. So using this equation, one can obtain integral fluctuation theorem and second law inequality during for the processes. Okay. Okay, so now let me move a bit to another development. I would like to tell you a bit about how we use this martingale theory also to obtain some results for quantum trajectories. And so to that, let me just introduce what are martingale processes. So martingale processes are stochastic processes. They have been introduced in probability theory by Paul Levy in 1934. And they are processes that just verify this condition here. So this means essentially that the expected, so if I am looking at some stochastic process M over time, and I record its values up to some time t, and then I ask, okay, what will be the expectation value of this process in the future, in any future time? So martingale processes are the ones in which the expectation value in the future is just the last value I observe. So they have no bias. So if I have to say what is the most likely value in the future, is just the last value I observe for that process. Okay, so these martingale processes are very well known in the mathematics of finance. They are used a lot there. We have seen also this morning that they can be used to ensure convergence in the quantum measurement process. And they verify many interesting properties. So here I just put two of them. So one is the Dup's optional stopping theorem, which states that the average of a martingale process at any stochastic time, meaning a random time, which is the first time that some condition is verified in your dynamics, is just the average on the initial state. So this is a very powerful equality. Then there is also Dup's maximal inequality that bounds the maximal excursions of this stochastic process by also the average, by the average of the process at some fixed time. So indeed, this is the time at the end of the interval you want to bound these fluctuations. So why we care about this here is because in classical stochastic thermodynamics, it has been shown that the entropy production in non-equilibrium steady states is a martingale process. And here I can recommend you this recent review by Edgar Roldan, also Raphael, and others, which appeared in Advancing Physics last year. So, so how to go with this into this framework that I presented to you of thermodynamics over quantum trajectories? So what happens, essentially, is that this is no longer true in the quantum case. And so the entropy production is no longer a martingale in non-equilibrium steady states over quantum trajectories. And, but what we obtain is that there is a piece of entropy production that will do that. Okay, and this essentially motivates a split of the entropy production in two terms. Okay, so we can define some part which we call uncertainty entropy production, which is essentially due to the generation of superpositions of eigenstates during the dynamics, during the stochastic dynamics. And then this martingale entropy production, that, as you may guess, is the part that will verify the martingale property. So the main idea is the following. Now, if you plot what will be the entropy production over time, so at the beginning, okay, it will be 0, and since you will be in some eigenstate of the dynamics, this is completely well defined. So here you have some jump, and then your entropy production changes, and so on and so forth. But however, as I explained before, the entropy production and also all the other quantities will depend on the final measurement of the two-point measurement scheme. So that whenever you generate some superposition of eigenstates, so the result of the entropy production will depend on that final measurement, final projective measurement. And this is what is represented here by these like green boxes. Because depending on the result of the final measurement, you may go here up or here down, right? So you may have different possible values. No? This is just a simulation in which we take a random some final measurement and get the result. So in this case, so how to define stopping times or stopping conditions? Because if I need to, so imagine I want to stop my process when the entropy production gets this value. But of course, if I trace the evolution and I arrive to this point, depending on the outcome of my final measurement, I will be up of this threshold or down, right? So what are the thermodynamic consequences of this? So essentially, when by introducing this split of entropy production, what we can do is to split this effect of this non-definition of the entropy production during the dynamics, and we do that by introducing this kind of entropy for superpositions, which is just minus the logarithm of the expectation value of the density matrix over the stochastic wave function. Okay, this is known in quantum information. This is called Schumacher's fidelity. Okay, using this is essentially the object that we use to define this uncertainty entropy production and this martingale entropy production. So as you can see, this martingale entropy production is like a classicalized version of the entropy production. So it uses this entropy for superpositions instead of just the logarithm of the probability of the final outcome. And doing that, you can see, for example, here in this plot, how this behaves. No? These blue parts will be the case if you perform the measurement, so you will have some random changes depending on whether you project or in 0 or in 1. And in dash, you can see what will be the value of this martingale entropy production. As you can see, go like interpolates between the possibilities, no? And it interpolates according to the weights of the superpositions you have during the evolution. Okay, so the point of this split is essentially that you will have all the good properties of entropy production for both parts, both the uncertainty part and the martingale part. So both of them verifies an integral fluctuation theorem. Both of them are positive at fixed time. But more importantly, for the case of the martingale entropy production, you get that this is a martingale, so you can prove this result. And this tells you essentially that, that you will have a fluctuation theorem at the stopping times. And if you go, so the consequence of this is that you will have this second law inequality at the stopping times, which means that if this quantity here is negative, so it can be negative at the stopping times, you will have like some extra kind of violation of the second law, right? Because you will have something here which can be less than 0. And this can be used indeed for gambling strategies and so on. So there is also, this is for non-equilibrium steady state, but this can be extended to transient dynamics and driving systems, which has been done in another reference. So yeah, how is time? I should finish. Okay, I had also this part of the non-detected jump, so imperfect detection. I will just go to the main point, which is essentially that when you go, so in this case, yeah, in this case, you no longer have the quality that I showed you before that relates the irreversibility and the energetics. Instead, so what happens when you have inefficient detection is that, so you can, the reversibility, which here will be this sigma, will be always a lower bound to the entropy production condition on the measurements that you obtain using the inefficient detection. So I don't have time to tell you about this, but if you are curious about this, just ask me and I will be happy to explain to you. Okay, so just as a conclusions, so stochastic thermodynamics can be formulated along quantum trajectories, and you will have quantum contributions both in the energetics and on the irreversibility. We can have fluctuation theorems at the stopping times with some quantum correction term. And then, so this will be for the last part, which is we can also obtain, in the case of inefficient detection, some conditional fluctuation relations that links entropy production and irreversibility, but not with an equality, okay, but with an inequality. And this may be used for lower bounding dissipation using irreversibility along single trajectories in which where the monitoring is not perfect. So yeah, essentially this is what I wanted to say. So thank you very much for your attention. And here I just put some of the references regarding the different parts of this talk.
Thank you for this talk. So is there some questions, please?
Hi, about the last thing you wrote about looking for experimental test. So here you demand full control on the Lindbladians as well, because they also a function of lambda, right? The Lindbladians.
You mean experimental?
Yeah, so the Lindbladian operators,
Yeah.
they're also functions of the control parameter lambda, right?
They may depend or not. Yeah, it depends on the setup.
So if you want that to be experimentally implementable, then that Lindbladians comes in this picture in terms of the measurements, the jumps, and the non-unitary evolution in between as well.
Yeah.
So the jumps I can imagine can be implementable, but now if you want to have that non-unitary evolution to implement, depending on that control parameter, then seems like in each bit between the measurement you have to introduce one ancillary system every time. Wouldn't that be very expensive?
I think that would be a way in order to get that. So using this ancillary system in which you measure before and after interaction. And so the fact that the Limrad operators get also, in principle, you move the, what you will do is to change the control parameter on the Hamiltonian. But depending on the interaction with the environment, that will imply also some dependence on the Limrad operators.
So only on the Hamiltonian control can achieve that use. Okay. Thanks.
So in the second part about the martingales, are you using the same dynamics of the first part? In particular, do you need the local detail balance condition, or is it more general?
It is more general, but today I wanted to stick to the case in which you have just thermal reservoirs as your environment, so that you can really identify heat very well and so on.
But in principle, you don't need it. I mean,
in principle, you can also formulate the same theory for non-thermal environments, and also the martingale part as well. So because it is constructed very much from the part of the reversibility, and this you can define whatever the environment is. Okay.
thank you.
But if you want to then to make the link with energetics, then you will need something like a thermal reservoir. Yep. Exactly. That is the part that will be a martingale. The other part is not a martingale, but it also verifies some fluctuation relation. So in particular, it verifies something like this, but with a 1 here always.
Gonzalo? Yeah, is there any way to generalize this to some non-Markovian dynamics?
This I don't know. I mean, I always assume Markovian dynamics in order to have this quantum jump approach. I mean, the point is that you will need to. Of course, there are some things that will be very basic and will apply to any process. But if you want like a differential equation, then I don't know how to obtain any other similar monitor quantum evolution with non-Markovian dynamics. You will need that. I mean,
yeah, I mean, one reasonably simple way might be that your Lindblad operators were dependent on time essentially. So in some in-between times, if some rates can become negative at some small times and then they become positive again or something.
Yeah, but in that case, I think the interpretation is not clear, no, for the quantum trajectories. But perhaps one way to do that is if you have again some like a scheme in which you have probes that interact with your system, and then you somehow reuse some of the probes or things like that, then you can start to see some Markovianity.
Okay, thanks.
Thank you. So if there is other questions, we can postpone them to lunch. And thanks again for your presentation.